Well, up till now, I suppose we've been learning about a lot of techniques for organizing big programs, symbolic manipulation a bit, some of the technology for what that you use for establishing languages, one in terms of another, which is used for organizing very large programs. In fact, the nicest programs I know look more like a pile of languages than like a decomposition of a problem into parts. Well, I suppose at this point, there are still, however, a few mysteries about how this sort of stuff works. And so what we'd like to do now is diverge from the plan of telling you how to organize big programs and rather tell you something about the mechanisms by which these things can be made to work. The main reason for this is demystification, if you will. We have a lot of mysteries left, like exactly how it is the case that a program is controlled, how a computer sort of knows what the next thing to do is, or something like that. And what I'd like to do now is make that clear to you, that even if you've never played with a physical computer before, the mechanism is really very simple, and that you can understand it completely with no trouble. So I'd like to start by imagining that the way we're going to do this, by the way, is we're going to take some very simple Lisp programs, and transform them into hardware. I'm not going to worry about some intermediate step of going through some existing computer machine language and then showing you how that computer works, because that's not as illuminating. So what I'm really going to show you is how a piece of machinery can be built to do a job which you've written down as a program. A program is, in fact, a description of a machine. We're going to start with a very simple program, proceed to show you some simple mechanisms, proceed to a few more complicated programs, and then later show you a not very complicated program, how the evaluator transforms into a piece of hardware. And of course, at that point, you've made the universal transition and can execute any program imaginable with a piece of well-defined hardware. Well, let's start up now, to give you a real concrete feeling for this sort of thing. Let's start with a very simple program. Here's Euclid's algorithm. It's actually a little bit more modern than Euclid's algorithm. Euclid's algorithm for computing the greatest common divisor of two numbers was invented sort of 350 BC, I think. It's the oldest known algorithm. But here we're going to talk about the GCD of A and B, the greatest common divisor of two numbers A and B. And the algorithm is extremely simple. If B is 0, then the result is going to be A. Otherwise, the result is the GCD of B, and the remainder when A is divided by B. So this we have here is a very simple iterative process. This is a simple recursive procedure, recursively defined procedure, or recursive definition, which yields an iterative process. And the way it works is that at every step, it determines whether B was 0. And if B is 0, we got the answer in A. Otherwise, we make another step where A is the old B, and B is the remainder of the old A divided by the old B. Very simple. Now, this, I've already told you some of the mechanism by just saying it that way. I said it in time. I said there are certain steps. And that, in fact, one of the things you can see here is that one of the reasons why this is iterative is nothing is needed of the last step to get the answer. All of the information that's needed to run this algorithm is in A and B. It has two well-defined state variables. So I'm going to define a machine for you that can compute GCDs. Now let's see, every computer that's ever been made that's a single process computer, as opposed to a multiprocessor of some sort, is made according to the same plan. The plan is the computer has two parts, a part called the data paths and a part called the controller. The data paths correspond to a calculator that you might have. It contains certain registers that remember things, and you've all used calculators, and has some buttons on it and some lights. Okay? And so by pushing the various buttons, you can cause operations to happen inside there among the registers, and some of the results to be displayed. That's completely mechanical. You could imagine that that box has no intelligence in it. Now, it might be very impressive that it can produce the sign of a number, but that at least is apparently, possibly mechanical. At least I could open that up in the same way I'm about to open GCD. So this may have a whole computer inside of it, but that's not interesting. Addition is certainly simple. That can be done without any further mechanism. Now, also, if we were to look at the other half, the controller, that's a part that's dumb too. It pushes the buttons. It pushes them according to a sequence which is written down on a piece of paper and observes the lights. And every so often it comes to a place in a sequence that says, if light A is on, do this sequence, otherwise do that sequence. And thereby there's no complexity there either. But let's just draw that and see what we feel about that. So for computing GCDs, what I want you to think about is that there are these registers. A register is a place where I store a number in this case. And this one's called A. And then there's another one for storing B. Now we have to see what things we can do with these registers. And they're not entirely obvious what you can do with them. But we have to see what things we need to do with them. We're looking at the problem we're trying to solve. One of the important things for designing a computer, which I think most designers don't do, is you study the problem you want to solve. And then use what you learn from studying the problem you want to solve to put in the mechanisms needed to solve it in the computer you're building. No more and no less. Now, it may be that the problem you're trying to solve is everybody's problem, in which case you have to build in a universal interpreter of some language. But you shouldn't put any more in than required to build the universal interpreter of some language. We'll worry about that in a second. Okay, going back to here. Let's see, what do we have to be able to do? Well, somehow we have to be able to get B into A. Okay, we have to be able to get the old value of B into the value of A. So we have to have some path by which stuff can flow, whatever this information is, okay, from B to A. I'm going to draw that by an arrow saying that it is possible to move the contents of B into A, replacing the value of A, and there's a little button here which you push which allows that to happen. That's what a little X is here. Now, it's also the case that I have to be able to compute the remainder of A and B. Now, that may be a complicated mess. On the other hand, I'm going to make it a small box. If we have to, we may open up that box and look inside and see what it is. So here I'm going to have a little box, which I'm going to draw this way, which we'll call the remainder. And it's going to take in A. And it's going to take in B. And it's going to put out something. The remainder of A divided by B. Another thing we have to see here is that we have to be able to test whether B is equal to 0. Well, that means somebody's got to be looking at a thing that's looking at the value of B. We'll have a light bulb here, which lights up if B equals 0. That's its job. And finally, I suppose, because of the fact that we want the new value of A to be the old value of B, and simultaneously the new value of B to be something I've done with A, and if I plan to make my machine such that everything happens one at a time, one motion at a time, and I can't put two numbers in a register, then I have to have another place to put one while I'm interchanging. Okay? I can't interchange the two things in my hands unless I either put two in one hand and then pull it back the other way, or unless I put one down, pick it up, and put the other one like that. unless I'm a juggler, which I'm not, as you can see, in which case I have a possibility of timing errors. And in fact, much of the type of computer design people do involves timing errors of some potential timing errors, which I don't much like. But so for that reason, I have to have a place to put the third thing down, the second one of them down. So we'll have a place called T, which is a register just for temporary, T, okay, with a button on it. And then I'll take the result of that, since I have to take that and put it into B over here, be able to take the result of that and go like this. And a button here. So that's the data paths of a GCD machine. Now, what's a controller? A controller is a very simple thing, too. The machine has a state. The way I like to visualize that is that I've got a maze. And the maze has a bunch of places connected by directed arrows. And what I have is a marble, which represents the state of the controller. The marble rolls around in the maze. Of course, if this analogy breaks down for energy reasons, I sometimes have to pump that marble up to the top because it's going to otherwise be a perpetual motion machine. But not worrying about that. Okay, this is not a physical analogy. This marble rolls around, and every time it rolls around certain bumpers, like in a pinball machine, it pushes one of these buttons. And every so often, it comes to a place which is a division where it has to make a choice, and there's a flap which is controlled by this. So that's a really mechanical way of thinking about it. Of course, controllers these days are not built that way in real computers. They're built with a little bit of ROM and a state register. But there was a time, like the DEC PDP-6, where that's how you built the controller of a machine. There was a bit that ran around in the delay line. Then eventually, and it triggered things as it went by, and it would come back to the beginning and get fed around again. And of course, there were all sorts of great bugs that you could have, like two bits going around. Two marbles, and then the machine has lost its marbles. That happens too. Oh well. So anyway, for this machine, what I have to do is the following. I'm going to start my maze here, and the first thing I got to do is, in a notation which many of you are familiar with, is b equal to 0, a test. And there's a possibility. Either yes, in which case I'm done. Otherwise, if no, then I'm going to have to roll over some bumpers. I'm going to do it in the following order. I want to do this interchange game. Now, the first instance, I need both A and B, but then and this is not necessary, I want to collect this. This is the thing that's going to go into B. So I'm going to say, take this, which depends upon both A and B, and put the remainder into here. So I'm going to push this button first. Okay? Then I'm going to transfer B to A, push that button, and then I transfer the temporary into B. Push that button. So, a very sequential machine. Very inefficient, but that's fine right now. We're going to name the buttons. T gets remainder. A gets B. And B gets T. And then I'm going to go around here and still go back to start. And if you look, what are we seeing here? We're seeing the various, what I really have is some sort of mechanical connection where T gets R controls this thing. Okay? And I have here that A gets B controls this fellow over here. And this fellow over here, boy, that's absolutely reverse. It's pessimal, the inverse of optimal. Every line had to cross every other line the way I drew it. I suppose this goes here. B gets T. Now I'd like to run this machine, but before I run the machine, I want to write down a description of this controller, just so you can see that these things, of course, as usual, can be written down in some nice language, so that we don't have to always draw these diagrams. One of the problems with diagrams is they take up a lot of space, and for a machine this small, it takes 2 blackboards. For a machine that's the evaluator machine, I have trouble putting it in this room, even though it isn't very big. So I'm going to make a little language for this. It's just a description of that. Say, define a machine we'll call GCD. Of course, once we have something like this, we have a simulator for it. And the reason why we want to build a language of this form is because all of a sudden we can manipulate these expressions that I'm writing down. And then, of course, I can write things that can algebraically manipulate these things, simulate them, all that sort of things that I might want to do. Perhaps transform them into layout. Who knows? Once I have a nice representation of registers, it has certain registers, which we're going to call A, B, and T. And there's a controller. Actually, a better language, which would be more explicit, which would be one which named every button also and said what it did. Like, this button causes the contents of T to move to the contents of B. But I don't want to do that because it's actually harder to read to do that. And it takes up more space. So I'm going to have that in the instructions written in the controller. Okay, it's going to be implicit what the operations are. Okay, they can be deduced by reading these and collecting together all the different things that can be done. Like we look at, say, well, let's look what these things are. There's a little loop that we go around, which says branch. This is the representation of the little flap that decides which way you go here. If 0, okay, fetch of B, the contents of B. If the contents of B is 0, then go to a place called done. Now, one thing you're seeing here, this looks very much like a traditional computer language. And what you're seeing here is things like labels that represent places in a sequence written down as a sequence. The reason why they're needed is because over here I've written something with loops. But if I'm writing English text or something like that, it's hard to refer to a place. I don't have arrows. Arrows are represented by giving names to the places where the arrows terminate and then referring to them by those names. Now, this is just an encoding. There's nothing magical about things like that. Next thing we're going to do is we're going to say, how do we do T gets R? Oh, that's easy enough. So assign. We assign to T the remainder. Assign is the name of the button. Okay, that's the button pusher. Assign to T the remainder, and here's the representation of the operation. When we divide the fetch of A by the fetch of B. Okay, we're also going to assign to A the fetch of B. Assign to B the result of getting the contents of T. And now I have to refer to the beginning here. I see. Why don't I call that loop like I have here? Okay. So that's that reference to that arrow. And when we're done, we're done. We go to here, which is the end of the thing. So here's just a written representation of this fragment of machinery that we've drawn here. Now, the next thing I'd like to do is run this. I want us to feel it running. Never done this before. You've got to do it once. Okay? So let's take a particular problem. Suppose we want to compute the GCD of A equals 30, okay, and B equals 42. I have no idea what that is right now, but A is 30 and B is 42. That's how I start this thing up. But what's the first thing I do? I say, is B equal to 0? No. Then assign to t the remainder of the fetch of a and the fetch of b. Well, the remainder of 30 when divided by 42 is itself 30. Push that button. Now I'm going, the marble has rolled to here. Okay. A gets B. That pushes this button. So the 42 moves into here. B gets T. Push that button. The 30 goes here. Or just interchange them. Now let's see. Go back to the beginning. B0, no. T gets the remainder. I suppose the remainder when dividing 42 by 30 is 12. So I push that one. Next thing I do is allow the 30 to go to here. Push this one, allow the 12 to go to here. Okay. Go around this thing. Is that done? No. How about, so now I have to find out the remainder of 30 divided by 12. And I believe that's 6. So 6 goes here on this button push. Then the next thing I push is this one, which the 12 goes into here. Okay. Then I push this button, the 6 gets into here. Is 6 equal to 0? No. Okay. So then, at that point, the next thing to do is divide it. Ooh, this has got a remainder of 0. Looks like we're almost done. Move the 6 over to here next. 0 over here. Is the answer 0? Yes. B is 0, therefore the answer is an A. Okay. The answer is 6. And indeed that's right, because if we look at the original problem, what we have is 30 is 2 times 3 times 5, and 42 is 2 times 3 times 7. So the greatest common divisor is 2 times 3, which is 6. Okay. Now normally we write one other little line here just to make it a little bit clearer, which is that we leave in a connection saying that this light is the guy that flap looks at. Of course, any real machine has a lot more complicated things in it than what I've just shown you. Let's look for a second at the first still store. Wow. Well, you see, for example, one thing we might want to do is worry about operations that are of the I/O form. And we may have to collect something from the outside. So the state machine that we might have, the controller, may have to, for example, get a value from something and put it into register A to load it up. I may have to load up register B with another value. And then later, when I'm done, I might want to print the answer out. And of course, that might be either simple or complicated. I'm writing assuming print is very simple and read is very simple. But in fact, in the real world, those are very complicated operations, usually much, much larger and more complicated than the thing you're doing as your problem you're trying to solve. Okay. On the other hand, I can remember a time when I remember using IBM 7090 computer of sorts, where things like read and write of a single object, a single number, a number, is a primitive operation of the I/O controller. Okay, and so we have that kind of thing in there. And in such a machine, well, what are we really doing? We're just saying that there's a source over here called read, which is an operation which always has a value. We have to think about this as always having a value which can be gated into either register A or B. And print is some sort of thing which, when you gate it appropriately, when you push the button on it, will cause a print of the value that's currently in register A. Nothing very exciting. So that's one sort of thing you might want to have. But there's also other things that are a little bit worrisome. Like I've used here some complicated mechanisms. What you see here is remainder. What is that? I mean, that may not be so obvious how to compute. It may be something which, when you open it up, you get a whole machine. Okay? In fact, that's true. For example, if I write down the program for remainder, the simplest program for it is by repeated subtraction. Because, of course, division can be done by repeated subtraction of numbers, of integers. So the remainder of n divided by d is nothing more than if n is less than d, then the result is n. Otherwise, the remainder when we subtract d from n with respect to d when divided by d. This looks just like the GCD program. Okay. Of course, it's not a very nice way to do remainders. You'd really want to use something like binary notation and shift and things like that in a practical computer. But the point of that is that if I open this thing up, I might find inside of it a computer. Well, we know how to do that. We just made one. And it could be another thing just like this. On the other hand, we might want to make a more efficient or better structured machine, or maybe make use of some of the registers more than once, or some horrible mess like that hardware designers like to do, and for very good reasons. So, for example, here's a machine that you see, which you're not supposed to be able to read. It's a little bit complicated. Okay? But what it is the integration of the remainder into the GCD machine. And it takes, in fact, no more registers. There are 3 registers in the data paths. Okay? But now there's a subtractor. There are 2 things that are tested. Is b equal to 0, or is t less than b? And then the controller, which you see over here, is not much more complicated, but it has two loops in it, one of which is the main one for doing the GCD, and one of which is the subtraction loop for doing the remainder sub operation. And there are ways, of course, of, if you think about it, taking the remainder program. If I take remainder, as you see over there, as a lambda expression, substitute it in for remainder over here in the GCD program, okay, then do some simplification by substituting a and b for remainder in there, then I can unwind this loop, and I can get this piece of machinery by basically a little bit of simplification, algebraic simplification on the lambda expressions. So I suppose you've seen your first very simple machines now. I wonder if there are any questions. Good. This looks easy, doesn't it? Thank you. I'm supposed to take a break.